Welcome to Deep Learning. Today we will talk about unsupervised learning. We will review a variety of techniques and try to understand how to be able to train a neural network without using a large amount of data. As we said at the beginning of this series, data is very important. Data is the king. It's the one that gives us the ability to train very powerful neural network models, and it's needed. But the problem is that labeling data is very costly because, like in cases like this, we have to collect large amount of information, for example, large amount of images, and have them labeled. In case of images, for example, it could be easy because people have been captioning images from their phone for many years now. There's many pictures on the internet. But in the case of video, this could be a daunting task. If, for example, we want to find 1,000 examples of a man picking flowers in a video. That does not exist readily. Labeling data is very costly. If we want to do the example we just mentioned, a person would have to sift through thousands and thousands of hours of video and watch them because there's no really automatic tool to do this. We need to find a way to go beyond this because there's a lot of information, for example, in videos. Take, for example, YouTube, where it has humans learn a variety of tasks by just watching the video. If we could harness all this information and be able to learn the information that is in videos, we would be able to create powerful robots that would help us on everyday life. Robots that could predict the future and understand our reality better. So supervised learning is extremely important. Another example that is very current, for example, is in autonomous driving. Think about the cost of labeling autonomous driving, where you have images like this that you have to label pixel-wise. Somebody has to sit down and manually draw a polygon on top of these images and mention the class name. And this has been done for, especially in this data set here, for example, for more than 5,000 images to date. Human self-labeling. It's very expensive. Could we do better than this? This is what we're talking about today. So somehow we need the self-labeled data. What is self-labeled data? Self-labeled data is some data that has a pattern that we can easily discern. Okay, that's easier said than done. What does it mean? It means that we need to figure out some properties of the data that allow it to self-label itself. For example, take an image. We could represent these images with a neural network with some kind of a code, but then we maybe, in order to train this neural network, we could try to reconstruct the input. That would be a way to do it. Also, it would be a very good way to remove noise and issues with the image. There are other techniques that we could use to label. For example, we might have other computer vision or techniques or something that already does something to the data, like tracking of an object or segmented image, that we could use to label our neural network or to label data. But let's be very careful with these techniques. This is actually often not a viable path, because those techniques that we want to use, like object tracker or image segmenter, often do not work very well or for every case. So they'll have a lot of false alarm and false positive. The data will have to be cleaned up. There's also a technique that you can think of taking your input and breaking it to pieces and creating a neural network that puts the pieces back together, so sort of solving a puzzle. This technique could be useful and interesting. Or you could use other sensor to label data. So as you're watching as you're looking at the street, maybe you could use a LiDAR or a laser scanner to basically measure depth of every object in the scene, and based on this depth you might be able to segment objects. Or maybe you don't know what they are, but at least it will help you to segment part of the object. But when there's a smooth transition, like in a road, it becomes more difficult. We could also bootstrap. So if we have a neural network that is trained to detect cats and dogs, for example, we could let it loose on thousands of images on the web so that it will find more cats and dogs. And we could use that data to train a bigger neural network or a more powerful neural network. And this is a great idea, but it has the problem of sometimes runaway issues. For example, neural network originally might not be able to detect some kind of dogs, and then never will, and so those dogs or those instances of objects might never end up in your training set. We need more constructive way to do unsupervised learning, and one of the goal of this lecture is actually to make you think about this issue, try to think about new ways, new constructive ways to create self-labeled data, because this is really a gold mine at this point. So for the last of this video, I would like to describe a few techniques that have been used in the past to do unsupervised learning. Okay, but maybe the really first one that have been thought for many years is autoencoders. So in autoencoders, you have an original input like this mnist digit. You have an encoder, so this is like a standard neural network or neural network layer that converts that image into some kind of compressed representation, smaller, but smaller number of bits than the input, maybe, but that is able also to be used by a decoder to actually reconstruct the input. So this is quite simple. You take an input, you have a network that compresses it, and from this compressed representation you want to reconstruct the input. So it's sort of like trying to find the base function of an image of an input, so that then you can reconstruct the signal, your input, out of this base function fairly easily. There's example code here, for example, in Torch, how to train an autoencoder. These are usually neural networks that are trained layer by layer. So this example that we show is just one neural network layer, because it's easy for us humans to kind of try to figure out how to reconstruct an image, and we can see, okay, this is the original image, this is reconstructed, looks good. So in a way, it makes it easy and more glorious to publish these results by being able to show that you can reconstruct something that is human consumable every layer. But in the second layer or the third layer, you might not be able to do something that people can understand. So it becomes a little bit more difficult and less glorious, I could say. Autoencoders are also, in the literature, are also thought as discriminating generative models, or a discriminative model, which is a standard neural network, is something that maps an input data X to a desired class Y. It does not have to be a desired class label, but usually it is. So you try to find the distribution, what is the probability of seeing Y given X. So instead of a generative model, which is the combination of a standard CNN like an encoder plus a decoder, is actually trying to learn the joint probability of the input data and the label simultaneously. So it's trying to learn the probability of X and Y together. So it's also very useful to generate new samples, which is actually very nice and attractive for us humans to see. And it's a more powerful maybe it's a more powerful technique because it's a technique that, as Geoffrey Hinton said, if you want to understand images, you need to be able to create images. That might be true to some extent. But yes, the idea is discriminative model, just a neural network, has its limitation. A generative model, something that can generate, hopefully has a better representation of the input, and this because it's able to reconstruct the input. Now, being able to reconstruct the input may or may not be important. It's important if you try to do segmentation or other low-level tasks that go back to the original image. But when you're thinking about building a representation of videos, for example, of actions, you don't necessarily need to reconstruct the input. Rather, you want a good representation that is able to be the same over a large variety of such examples. Nevertheless, a generative model, especially in deep learning, have become very popular in the last couple of years. Speaking of autoencoders, came out from neuroscience and theoretical research on sparse coding. So sparse coding basically is a theory that says, okay, the brain must be creating some kind of a base function, and it must use these base functions in the best possible way, meaning it needs to minimize the activation of this base function in order to preserve energy. So you don't want the brain to consume a lot of energy when it's active. And so if you take into account the concept of energy, you could translate it into concept of sparsity. So you want this base function of the representation to be sparse, meaning to be as minimally active as possible, right? So if you take basically an input vector x, you can represent it as a linear combination of some base functions, phi I, right? And this kind of sparse coding can simulate actually quite well the representation that we see in the brain, especially in the first layer V1 of the visual cortex, where you have filters that look like this image. And sparse coding, if you want to define a cost function too, it's basically this. So you want to minimize, the combination of coefficient A, which are the weights, that you use to recombine, and you also want to find the optimal base function. That basically the first term give you a good reconstruction of the input. So you want it for all the items in your data set, all the xj, you want to find basically the best possible error. So this is like an error between the input and the representation. And the second term is instead basically states, that we want sparsity, and we want this A to be as little as possible. So we're trying to force them to be as close as possible to zero, right? And doing this kind of minimization is actually quite expensive, but it's been done many times. People have found techniques to do one layer at a time, and this is basically one of these techniques is basically similar to autoencoders. So in general, autoencoders and sparse coding have the advantage of being quite simple. So there's simple techniques where you can reconstruct the input. And also you can stack multiple layers. So once you found the representation of the first layer, then you can use this representation to go to a second layer and reconstruct the first layer representation. So you can stack them like this. It's intuitive, and also it's based on neuroscience research, which is nice. Because it tries to also explain how our brain works. But there are some disadvantages. So first of all, each layer is training greedily. So you have to train one layer at a time. There's no global signal. So that might be compatible with neuroscience maybe. But the fact that there's no global optimization gives you suboptimal results. In fact, these techniques never were able to match the performance of supervised learning. You have to understand another thing about this comment, though, is that supervised learning in the last 5 years has grown so fast. We have so much images and so much label that it's very hard to do, especially categorization like ImageNet or segmentation like autonomous car driving, or the basic categorization of object in images. It's very hard to beat supervised learning because there's so much data available, and the optimization techniques are simple. You just train a network, right? So here we're trying to do something more complicated. Once we try to have data with no labels, which is causing a problem. Second, we try to train layer, with not a categorization cost function, but more like a reconstruction cost function, which may or may not give you the best representation, as we said before. And third, we're trying to stack multiple of these layers together. And we really don't know how to do this effectively, and we're still learning to do this. So multiple layers of this network are been quite ineffective. I have not seen examples that really gave great performance. And like I said, also reconstructing the input may not be an ideal metric for learning a general purpose representation, because reconstructing the input requires a lot of power and computation that you might not need. Try to think of, for example, of a familiar scene in your house, right? Or a room, your room or your bedroom, right? You are able to actually remember things about your bedroom, but I don't think if I ask you to draw it down with photographic precision that you can do it. Maybe in our brain, some people can do this, by the way, these are called artists, but I think in general our brain is not designed to perfectly reconstruct the input, but rather to have enough information. Where is my bedroom, where is my lamps, where is the switch, more or less, which is the 3D organization. So you're learning compressed representation, basically, and this is actually what we're after, really. Next, we'll talk about clustering learning. So clustering learning is something that our lab worked quite a lot in the last 5 years. It came out from a really simple but quite effective idea. The one of basically trying to figure out how to do Hebbian learning with neural networks. So as you know now, neural networks are trained with gradient descent, while instead that is something that globally the whole network is trained together, based on an error at the output, and you backpropagate to the input. As far as we know, and we're still studying this, the human brain does not learn like that. It more like learns in terms of, they say that neurons that fire together, fire together usually develop a stronger connection between the two. Usually what it means is if a neuron, upstate neuron is stimulated by another neuron, if the second neuron is going to fire very quickly after the first neuron, then their connection strengthens, because there's some causality connection between the two. So we thought that, and we were not the only one, but we thought that clustering inputs together would do something similar. So for example, if we had a representation at the first layer that the output, two outputs, for example, would be similar, would have a similar kind of response, that then it would make sense to group them together because they are responding to the same stimulus. And this also imposes some sparsity constraint, because it forces you to group things that are similar into just a set of base functions. So let me show you an example here. So this is an example of what you can do, in order to learn these filters. So you can basically, the idea was to take random patches of the input data, okay, and then pick one example and average the example with very similar ones, and then continue. After a while, actually, you basically get this kind of representation where your patches end up looking very similar to V1 filters in the brain. So what we did is we take random patches of images, so the input, and then we cluster them together. And then what we do is, if you think of a neural network layer, so that does convolution, max pooling, and ReLU, we use these filters for the convolution. It turns out that this is a very fast technique because you're just clustering bits of the inputs. So it takes five minutes. It's really so much faster than training supervised. Even for just one layer. But the problem comes when you think about the second layer. Okay, now I learned one layer, right? And now I'm going to a second layer. How do I connect the features of the first layer to the features of the second layer? So, in standard deep neural network model, these are all fully connected, and then you let the neural network training and to sort of figure out which of these connections are good, and usually uses most of them, and maybe some are more efficient than others. But here we don't have this global training, right? So we are just clustering layer by layer. So what can we do? So what we can do is we can compute sort of the covariance matrix of maps. So once we figure out maps after the first layer, we form basically a group of maps that are the most similar. And these maps that are the most similar, we group them together. So we say, okay, all of these guys will have a parameter and add together into the next layer. And then we cluster. We repeat this clustering technique that we did before, so taking patches of these groups, and we create the next layer filter. So in other words, basically if we have n maps coming out of the first layer, so n1, then what we do is we group them together, and then we group them together and we create some filters based on clustering them, these groups. So each group is clustered together. Patches of the groups are form the filters that are then going to use to filter the original images into the maps of the next layer. So this is a technique that clusters the input based on concurrence of features. And you can repeat this for multiple layers. So you take one input, you cluster things together, you form filters for the convolution, and then you create a set of output maps. You cluster these inputs again, and you generate the outputs. And then you can repeat this multiple times, just like it's done for stacked autoencoders. So what we found out when we first did this experiment about 5 years ago is that at least with 2 layers, the results were comparable to standard CNN and COMNET. They were very similar. But when you were adding a third layer or a fourth layer, the result started to become less interesting. Another one of us, Isaac Dundar, who graduated in May 2016, also did some experiment, extended this work to do clustering learning, so to try to use a supervised technique to figure out how supervised technique would connect the layers together, and based on little data, and use that information to use clustering learning and some supervision to basically get really good result on the dataset STL10, which is a dataset that has very few example for training, and usually deep neural net fail to get good result on it because there's just not enough data to train all the parameters. But with unsupervised techniques, you can pre-train on this large data set on a much larger group of data that is not labeled, and then test on this and show that actually you get better results. So Isaac got better results by using this clustering learning, convolutional clustering technique. Also, it's quite interesting to notice that if you cluster patches for multiple frames, so the same patches, multiple frames, so actually you could get motion filters. So you basically get filters that move in time, like the one that you see here. So this is quite interesting because it would allow to use clustering learning for learning motion filters that could be used in movies. You can also do topographic filters by imposing a constraint that you can arrange, for example, your filters to be on a 2D map, and then you forced to close filters that are close to another filter have to be fairly similar. So impose another constraint in sparsity, so not only they have to be sparse and grouped together, but you also want them to cluster in a way that similar filters are closer together. And then you get this nice pattern, a pinwheel pattern that other people have shown. This again, they look really nice, but they never really found a great application. But this kind of pinwheel arrangement is also found in the human brain. So it makes a nice, interesting parallel, although we have not been able to really use it. So to summarize, clustering learning has the advantage of being a simple technique. It clusters similar outputs together and is able to stack multiple layers. So you can have a complex neural network with multiple layers. It's intuitive and it's based on neuroscience research and Hebbian learning, derivative of Hebbian learning model. The disadvantages of those are that each layer again is trained greedily without the global optimization that seems to really penalize the network. In some cases, it matches the performance of supervised learning. It can beat it if you have not enough data. But multiple layers become increasingly inefficient, and this is a problem of most of these techniques, like the stacked autoencoders and clustering learning, that are trained greedily. So having one layer is very nice and effective. Second layer adds a little bit, and after you go to 3 or 4 layers, it's just not, doesn't really give you an advantage. So people have this technique have their limitation. What people get very excited about in the last 2 years is the generative adversarial network, or GAN, which are basically very interesting. It's a very interesting idea. The idea is this: let's train an entire neural network now, not just one layer at a time. Let's train this neural network by make it play a game. Okay. So these are this neural network both have a discriminator and a generator. So similar to what we've seen before, it's really a generative model. So you can also discriminate. It's like a conventional neural network, but it has a generator, which is sort of like the opposite of the neural network. It takes a representation and upsamples it back to the original image, try to reconstruct the image. Okay. Now, the idea now is to feed unlabeled data, so of some specific kind. So for example, just to take a lot of images of a bedroom, or take a lot of images of faces, okay, and then send it to this discriminator. At the same time, have the generator create random images, create some images, right? And then what you want to do is train the discriminator to do a very simple task. Like, he has to basically figure out if you are giving it as an input a real sample or one generated by the generator. Okay. And when you train both the discriminator and the generator to do a good job on this task, basically you force the generator to start to produce very good representation of your input, as simple as close as possible to the data sample. You also train a discriminator to really tell a fine difference between the generated images and the real images. So then you get things like this. So these are examples of generated bedrooms that, if you look at them, globally, they look really okay. It really looks like a room or a bedroom. If you look in details, you might find, that they have the parts, the interesting things of the bedroom, but maybe they're not completely there yet. But up here you can see the generator network. So this generator network, in this case of the gun, it takes a random vector actually, and it basically creates has multiple. It's like a neural network in reverse, where we use convolutions to upsample and unpooling, max unpooling, or average upsampling to upsample the image back to the original input. And after you train this neural network on something specific, you get really cool things. So, for example, if you train them on faces, you can even get really cool representation. So, where cool, interesting property of the representation, where if you subtract, for example, smiling women to neutral women, and you add neutral men, these are all representation, by the way. So if you look at the representation space and you take a smiling woman representation minus the neutral woman representation plus the neutral man, you actually get the smiling man. So you can actually do operation in this space that it learns. That makes you think that it groups things together that are similar. They have similar concept. This is similar to what has been done also in speech recognition and models of language. And you can see you can do the same thing with glasses below. A man with glasses minus a man without glasses plus a woman will give you women with glasses. It's very interesting. Also, if you can move slightly one variable of this random variable at the generator, and it will smoothly give you variation, for example, in the bedroom. So it will slowly vary one image into another. And this is actually a sequence. If you look, every row continues to the next row. So by just changing a few parameters, you can get a whole spectrum, and they're all grouped together very nicely. So the representation of similar things is grouped together. This gave us a lot of excitement for this technique, because you thought, okay, well, that is really exactly what I wanted to do. I wanted to have a representation that cluster things together and I could do operation with. So I got a lot of people very excited. They're still at the very bleeding edge of deep neural network as of today. At the same time, people have also used generative adversarial network to do captioning of images. So in this case, people at Michigan Hongkak Lee have taken a caption and turned them into a random vector plus representation of the caption to generate an image. And then the discriminator network is the same. It takes an input and the caption, and you want to see that whether the input has been created again by the generator or it was a real input and a real caption. So obviously you use the same caption for both sides, but you basically train this neural network to provide you both a caption and also reconstructed images, which is very nice. So they can, if you give them a caption, they can create very similar images. And this is also, it sort of primes that input random vector to the generator, which is maybe one of the issues that have been always discussed about generative network, which is, we would like the representation of the output to be controlled rather than determined randomly by random number, right? In my view, the generative adversarial network had the advantage of training globally the entire network, so you get a good neural network that is trained to do any task, right? It's also a fairly simple to code and implement this whole GAN generative adversarial network, and we provided some examples here in Torch. it's a very simple code, but it has the disadvantage that it's hard to train. There's some conversion problem, obviously, because at the beginning the generator is generating garbage out of random noise, and it needs to sort of figure out that it needs to generate something similar to the input. So as you can think, it's not an easy task. Right, but there's a lot of new articles and new work now that show how to improve this. In some cases, this technique also matches the performance of supervised learning, especially if you don't have a lot of samples. People have shown that it could be used as a good representation, but I think we would like to see more. We need to prove more the usability of the representation, and this is really a problem of all unsupervised algorithms in a way. Next, we will discuss self-labeled data. So in this case, for example, in this work, people have taken an image from the left and tried to reconstruct an image from the right, again with an encoder-decoder architecture, very similar to what we've seen before. And they're able to generate from a single image, they're able to generate very interesting the ability to sort of turn them into 3D, which is quite cool. More interesting, I think, is self-labeled data is a simple task of predicting the next frame in a video. I think this has a big advantages, and it's quite usable and quite easy to do. So it's in a way similar to an autoencoder, right? Where you're trying to reconstruct the input. But now instead of reconstructing the input, you look at a few frames in the video and you try to predict a future frame. Okay, this is easier said than done, but in a paper from MIT, for example, what they do is they create a neural network with 5 convolutional stage, fully connection that is similar, I think, to an AlexNet, and then also they feed this current frame to this network, and then they feed the future frame to a pre-trained neural network like a Google Net or AlexNet or something. And basically they want to find something that minimizes the error between the prediction of the network being trained, which is trying to predict next frame, and the actual frame. So but they actually try to minimize the error between the representation. So this is interesting work. It has a couple of disadvantages, though. So one of them is that you're getting a representation for a pre-trained AlexNet and GoogleNet, which really is trained on still images, so it doesn't have any concept of moving information, right? And there's no recurrency here over time, although you could take multiple frames. You can take multiple frames here, this k value, and group them together. But there's really, the network is not trained to combine this representation over time, so it's a bit redundant, and it's maybe over-engineered, but it had pretty good results, and it's a fairly good and simple approach. Just to take a neural network that was already trained and train another neural network to globally to predict the next frame. So it's sort of like a combination of autoencoder on steroids on video. What I think is much more interesting instead is the PredNet by the Cox lab, which actually is a very interesting neural network that is really quite bio-inspired. It's designed by this idea of predictive coding. So it puts together all the concepts that we've seen before. So supervised learning, self-learning, grid layer by layer, and the idea of recurrency and the idea of predicting the next frame in the best possible way. So it puts them all in basically a quite simple model. So you can see the diagram in the middle of these images. This is one layer of the neural network. So what it does, is it takes an input at the bottom here in this blue box, and it does one standard layer of a convolution. So just convolution, and pooling, and then basically it subtracts it to another blue module on top that is supposed to do prediction. And here you try to, in the red box, you try to take the error of these two. So you subtract the two and then you add a ReLU to make sure that you can add another layer. Basically, this is your output, but your output is going to the next layer. So this is an error output. Is the difference between your input that what you would like reconstruct and a reconstruction. This output goes to the next layer, but also it feeds back to a very important module, this green module, which is a convolutional LSTM module. So this basically combines convolutional layer with a recurrent neural network. So it makes it, it's a recurrent convolutional layer of some kind that it not only that basically remembers sequences, it remembers something about the past. So this is a quite efficient representation. It sort of has the most minimal blocks to do predictive coding at every layer. So that at every layer it has a little mini neural net that takes the input and generates a representation. This time it has a block that remembers previous frames and into some representation of the error, and uses this representation to predict the next frame, to predict the same frame. And then there's an error module. So the interesting thing about this error module is that this whole layer here embeds both a layer but also the criterion for the layer. So the criterion here is, in this case, would be to minimize the error. So you want the output to be minimal. So advantages of this network are that has a self-embedded loss. If you want to stack two layers, then you can look at the diagram on the left, where two layers are stacked. You can stack more layers, up to 3 or 4 have been shown recently. And look at the results that the PredNet, this model is called PredNet, obtains on images of street scene, for example. Is able to predict really nicely how things are going to move in space, and even shades, shadows, how they're moving. So it predicts very effectively. And if you look at the second video, it predicts what moves and how it moves, and it predicts what stays still. So it has a pretty good idea of what's an object, what's a background, and how things move in space and time. This is, I think, a 3-layer neural network. So these results are quite exciting, and my opinion may be the most exciting up to date. If you look at an example of how it will predict multiple frames, so you can prime it with the sequence, and then you can let it predict t+1, t+2, t+3. Obviously, it becomes a little bit more blurry as you predict the future, because the future is unclear. You don't know what exactly is going to happen. But the results are quite nice, and I would say they show that the representation that this neural network learns is very effective to separate objects and to really learn the properties, not about spatial property, but also spatial temporal properties. This network is also a pretty good model of what could happen in the brain, where you have recurrency and feedback. You have feedback from higher nodes into lower nodes. So in fact, all these recurrent modules in green, if you look at the left image, they actually feed on themselves from the top down. So they provide feedback about what happens, representation in higher level to bottom layer. So it's quite effective model. The advantages of this model are that it creates a neural representation that can extend beyond just a single frame of supervised CNN. It can use unlabeled data. So this neural network is trained on just a video stream that are similar, similar content. That's all you need. And yes, it costs twice the computation, because you have a generator branch, and okay, you have some kind of LSTM as well. So it could be quite heavier than a single supervised learning. But he has the ability of continuously learning and adding knowledge, probably without the need to constantly add. If you want to add more features, you can add more videos, and you will learn the statistics of these videos as well. Also, the learning of loss function is embedded in the neural network, so you don't need to add another computational module. He also is able to do online learning by monitor the error signal. So if he has seen if the input is known to it, so he's seen similar things, the error will be low. But when you have a very high error, then it means that this is something that the network does not know, and then it could be used as a training. So it's a kind of an extendable network, as opposed to standard convolutional neural network, where you're able to make it learn more, and you have a signal that tells you when to do so, which is something that did not happen in previous neural network. I think we also has the ability to improve temporal coherence, invariance to perspective, and adversarial noise. He will also has the power to create a powerful representation that seems to be doing tracking, segmentation, and scene parsing all at once. And he also combines bidirectional models of the human brain. These are all things that still need to be proven, but they're very exciting about this kind of research. So now we have a temporal convolutional neural network that are both forward and feedback. So I hope this would a basic introduction of unsupervised techniques. My recommendation is to look for papers about this if you're interested. They keep coming out at a very high rate, so once every month or two you'll see something. And I would highly recommend you to think about your own way to create self-labeled data or task that would self-label the data, because this is a very important task.